When adding a new meter for a 20 amp house panel for a new fire alarm system to an existing 800 amp apartment meter center with 12 meters, the feeders from the existing meter center 800 amp main to the new meter do not need to be sized at 800 amps, nor do they need to be exactly 20 amps. The National Electrical Code, or NEC, provides guidelines for determining the appropriate feeder size based on the load characteristics. According to the NEC section 220.10b, the feeder conductors shall have an ampacity not less than that of the sum of the non-continuous loads plus 125% of the continuous load. For a feeder supplying more than one unit, the feeder conductors shall have an ampacity not less than the sum of the maximum demand of all units or spaces supplied, NEC 220.82. Understanding the difference between continuous and non-continuous loads is crucial. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Examples of continuous loads include lighting in commercial buildings, heating systems, and certain types of machinery. In these cases, the feeder must be sized to handle 125% of the continuous load to account for the sustained demand. A non-continuous load, on the other hand, is a load where the maximum current is not expected to continue for 3 hours or more. Examples of non-continuous loads include general receptacle circuits, intermittent machinery, and in this specific case, the fire alarm system. For non-continuous loads, the feeder only needs to be sized to handle the load's ampacity without the additional 25%. In this particular scenario, the new fire alarm system is considered a non-continuous load because its maximum current draw is not expected to continue for 3 hours or more. Therefore, the feeder ampacity does not need to be greater than its own load rating. Given that the fire alarm system has a load rating of 20 amps, the feeders from the existing meter center 800 amp main can be sized at 20 amps to supply the new meter. It is important to note that while the NEC allows for sizing the feeders at 20 amps, it is always a good practice to consider future expansion and potential increases in load. If there is a possibility that the fire alarm system will be upgraded or expanded in the future, it may be prudent to install feeders with a slightly higher ampacity to accommodate the potential increase in demand. Additionally, the feeder installation must comply with all other applicable NEC requirements, including those related to conductor type, insulation, and overcurrent protection. Conductors must be suitable for the application and installed in accordance with the NEC wiring methods. Overcurrent protection, such as circuit breakers or fuses, must be provided to protect the conductors from overload and short circuits. The overcurrent protection device must be sized to protect the conductors while also allowing for the fire alarm system's inrush current during startup. Furthermore, it is essential to ensure that the existing 800 amp meter center has sufficient capacity to handle the additional 20 amp load of the fire alarm system. A load calculation should be performed to determine the total load on the meter center and verify that it does not exceed its rated capacity. This load calculation should take into account all existing loads, as well as the new fire alarm system load. If the load calculation indicates that the meter center is nearing its capacity, it may be necessary to upgrade the meter center or implement load management strategies to prevent overloading. In summary, when adding a new meter for a 20 amp fire alarm system to an existing 800 amp meter center, the feeders can be sized at 20 amps based on the NEC guidelines for non-continuous loads. However, it is crucial to consider future expansion, comply with all other applicable NEC requirements, and ensure that the existing meter center has sufficient capacity to handle the additional load. Always consult with a qualified electrical engineer or electrician to ensure that the installation meets all applicable codes and standards and is performed safely and correctly. The NEC, or National Electrical Code, is a comprehensive set of standards and guidelines for electrical installations. It is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. Understanding and adhering to the NEC is essential for ensuring the safe and reliable operation of electrical systems. In addition to feeder sizing, the NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important to familiarize yourself with the NEC requirements that are relevant to your specific project. When sizing feeders, it is also important to consider voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To minimize voltage drop, it may be necessary to increase the size of the conductors. The NEC provides tables and formulas for calculating voltage drop based on conductor size, length, and current. Grounding is another critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock. The NEC requires all electrical systems to be properly grounded. Grounding electrodes, such as ground rods or ground plates, must be installed and connected to the grounding system. The size and type of grounding electrode must comply with the NEC requirements. Overcurrent protection is essential for protecting conductors and equipment from overload and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. The NEC requires overcurrent protection devices to be sized to protect the conductors they supply. The overcurrent protection device must have an ampacity rating that is equal to or less than the ampacity of the conductor it protects. In addition to the NEC, local codes and regulations may also apply to electrical installations. It is important to check with your local building department to determine the specific requirements in your area. Local codes may be more stringent than the NEC in some cases. When working with electrical systems, it is always important to prioritize safety. Electricity can be dangerous, and it is essential to take precautions to prevent electrical shock and other hazards. Always energize circuits before working on them. Use insulated tools and equipment. Wear personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, hire a qualified electrician to do the work for you. In the context of adding a new meter for a fire alarm system, it's also worth discussing the specific requirements for fire alarm circuits. Fire alarm systems are considered life safety systems, and they have special requirements in the NEC to ensure their reliability and functionality during a fire. The NEC Article 760 covers the requirements for fire alarm systems. Some key considerations for fire alarm circuits include, firstly, wiring methods. Fire alarm circuits must be installed using wiring methods that are suitable for fire alarm systems. These wiring methods typically include metal conduit, mineral insulated cable, or other approved methods that provide protection against physical damage in fire. Secondly, circuit integrity. Fire alarm circuits must maintain their integrity during a fire. This means that the circuits must be able to continue operating even if the building's power supply is interrupted. To achieve this, fire alarm systems often use backup power supplies such as batteries or generators. Thirdly, supervision. Fire alarm circuits must be supervised to detect faults, such as open circuits or short circuits. Supervision is typically achieved using end-of-line resistors or other monitoring devices that continuously check the integrity of the circuits. Fourthly, separation. Fire alarm circuits must be separated from other electrical circuits to prevent interference and ensure their reliability. The NEC requires fire alarm circuits to be installed in separate raceways or cable trays from other circuits. In addition to the NEC requirements, fire alarm systems must also comply with the National Fire Alarm Code, or NFPA 72. NFPA 72 provides comprehensive guidelines for the design, installation, and maintenance of fire alarm systems. It covers topics such as system performance, alarm notification, and emergency communication. When adding a new fire alarm system, it is important to consult with a qualified fire alarm technician to ensure that the system meets all applicable codes and standards. The fire alarm technician can help you select the appropriate equipment, design the system layout, and install the system correctly. They can also provide ongoing maintenance and testing services to ensure that the system remains in good working order. In summary, when adding a new meter for a fire alarm system, it is important to consider the specific requirements for fire alarm circuits in the NEC and NFPA 72. These requirements are designed to ensure the reliability and functionality of fire alarm systems during a fire. Always consult with a qualified fire alarm technician to ensure that the system meets all applicable codes and standards. Moreover, the discussion on feeder sizing is closely tied to understanding load calculations as a whole. Load calculations are a fundamental aspect of electrical design and are essential for determining the appropriate size of feeders, service conductors, and overcurrent protection devices. The NEC provides detailed guidelines for performing load calculations in Article 220. The basic principle of load calculations is to determine the total amount of power that an electrical system is expected to draw. This is done by adding up the individual loads of all the electrical equipment and devices that will be connected to the system. The NEC provides different methods for calculating loads, depending on the type of occupancy and the type of loads involved. For example, the NEC provides specific load calculation methods for dwelling units, commercial buildings, and industrial facilities. The NEC also provides different load calculation methods for different types of loads, such as lighting, receptacles, appliances, and motors. One important aspect of load calculations is to distinguish between continuous and non-continuous loads, as previously mentioned. Continuous loads are those that are expected to operate for 3 hours or more, while non-continuous loads are those that are not expected to operate for 3 hours or more. The NEC requires continuous loads to be multiplied by 125% when calculating the total load. This is to account for the fact that continuous loads can cause conductors and equipment to heat up over time. Another important aspect of load calculations is to consider demand factors. Demand factors are multipliers that are applied to the total load to account for the fact that not all electrical equipment will be operating at the same time. Demand factors are based on statistical data and are intended to reflect the actual usage patterns of electrical equipment. The NEC provides demand factors for different types of occupancies and different types of loads. After calculating the total load, the next step is to determine the appropriate size of the feeders, service conductors, and overcurrent protection devices. The NEC provides tables and formulas for determining the ampacity of conductors and the interrupting rating of overcurrent protection devices. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The interrupting rating of an overcurrent protection device is the maximum amount of current that it can safely interrupt without failing. When selecting conductors and overcurrent protection devices, it is important to choose those that have ampacity and interrupting ratings that are equal to or greater than the calculated load. It is also important to consider voltage drop when selecting conductors. As previously mentioned, voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuit. In summary, load calculations are a fundamental aspect of electrical design and are essential for determining the appropriate size of feeders, service conductors, and overcurrent protection devices. The NEC provides detailed guidelines for performing load calculations in Article 220. When performing load calculations, it is important to distinguish between continuous and non-continuous loads, consider demand factors, and account for voltage drop. Always consult with a qualified electrical engineer or electrician to ensure that load calculations are performed correctly and that the electrical system meets all applicable codes and standards. And in this particular situation, the concept of diversity can also play a role. Diversity, in the context of electrical load calculations, refers to the likelihood that not all loads within a system will be operating at their maximum capacity simultaneously. This is particularly relevant in multi-unit dwellings or apartment complexes where individual units may have varying usage patterns. The NEC recognizes diversity and allows for the application of demand factors, as mentioned earlier, to account for this phenomenon. Demand factors are essentially multipliers that reduce the overall calculated load based on the assumption that not all loads will be operating at their peak at the same time. These factors are derived from statistical data and reflect typical usage patterns in different types of occupancies. For example, in an apartment complex, it is unlikely that all residents will be using their air conditioners, ovens, and other appliances at the same time. Therefore, a demand factor can be applied to the total calculated load to arrive at a more realistic estimate of the actual demand. However, it is crucial to apply demand factors judiciously and in accordance with the NEC guidelines. Overly aggressive application of demand factors can result in undersized feeders and service equipment, which can lead to overloaded circuits and potential safety hazards. It is important to carefully consider the specific characteristics of the occupancy and the types of loads involved when determining the appropriate demand factors to use. In the case of adding a new fire alarm system to an existing apartment meter center, the diversity of the existing loads may be a factor to consider. However, the fire alarm system itself is typically considered a non-coincidental load, meaning that its operation is not dependent on the operation of other loads. In other words, the fire alarm system must be able to operate reliably regardless of whether other loads are running or not. Therefore, it is generally not appropriate to apply diversity factors to the fire alarm system load when calculating the total load on the meter center. The fire alarm system should be treated as a dedicated load that must be fully supported by the electrical system. In addition to diversity, another factor to consider is the potential for future expansion. Electrical systems should be designed with some degree of spare capacity to accommodate future growth or changes in load requirements. This is particularly important in commercial or multi-unit dwellings where there may be a need to add new tenants or equipment in the future. When designing an electrical system, it is advisable to include a contingency factor to account for potential future expansion. A contingency factor is a percentage increase that is added to the calculated load to provide a margin of safety and to allow for future growth. The appropriate contingency factor will depend on the specific characteristics of the occupancy and the likelihood of future expansion. In summary, diversity and the potential for future expansion are important factors to consider when designing electrical systems. Diversity allows for the application of demand factors to reduce the overall calculated load, while a contingency factor provides a margin of safety and allows for future growth. However, it is crucial to apply these factors judiciously and in accordance with the NEC guidelines to ensure that the electrical system is properly sized and can safely and reliably support the intended loads. And also remember the importance of coordination studies in larger electrical systems. Coordination studies are an essential aspect of electrical system design and are particularly important for larger or more complex systems, such as those found in commercial buildings, industrial facilities, or multi-unit dwellings. A coordination study is a comprehensive analysis of the electrical system's protective devices, such as circuit breakers and fuses, to ensure that they are properly coordinated to minimize the extent of any potential fault or overcurrent event. The primary goal of a coordination study is to achieve selective coordination, which means that the protective devices closest to the fault should trip first, while upstream devices remain closed. This minimizes the disruption to the electrical system and prevents unnecessary outages. Selective coordination is particularly important for critical loads such as fire alarm systems, emergency lighting, and life support equipment, which must remain operational during a fault. A coordination study typically involves the following steps. Firstly, data collection. The first step is to gather detailed information about the electrical system, including the size and type of conductors, the ratings of protective devices, and the impedance of transformers and other equipment. Secondly, modeling. The electrical system is then modeled using specialized software to simulate the flow of current under various fault conditions. Thirdly, analysis. The software is used to analyze the performance of the protective devices under different fault scenarios and to identify any potential coordination problems. Fourthly, recommendations. Based on the analysis, recommendations are made to adjust the settings of the protective devices or to replace devices that are not properly coordinated. Fifthly, documentation. The results of the coordination study are documented in a comprehensive report, which includes detailed diagrams, calculations, and recommendations. Coordination studies are typically performed by qualified electrical engineers who have expertise in power system protection and coordination. The results of the coordination study should be reviewed and approved by the building owner or facility manager. In the context of adding a new fire alarm system to an existing apartment meter center, a coordination study may be necessary to ensure that the new fire alarm system is properly coordinated with the existing electrical system. The coordination study should take into account the specific characteristics of the fire alarm system, including its fault current contribution and its sensitivity to voltage dips. The coordination study should also ensure that the fire alarm system's protective devices are properly coordinated with the utilities' protective devices to prevent nuisance tripping of the utilities equipment. In addition to coordination studies, arc flash studies are also an important aspect of electrical safety. Arc flash is a dangerous phenomenon that can occur when there is a fault in an electrical system. An arc flash is a sudden release of energy in the form of heat, light, and pressure, which can cause severe burns, injuries, and even death. Arc flash studies are performed to assess the potential hazards associated with arc flash and to develop strategies to mitigate those hazards. An arc flash study typically involves the following steps. Firstly, data collection. The first step is to gather detailed information about the electrical system, including the size and type of conductors, the ratings of protective devices, and the impedance of transformers and other equipment. Secondly, modeling. The electrical system is then modeled using specialized software to simulate the arc flash event. Thirdly, analysis. This software is used to analyze the potential arc flash hazards, including the incident energy, the arc flash boundary, and the required personal protective equipment, or PPE. Fourthly, recommendations. Based on the analysis, recommendations are made to reduce the arc flash hazards, such as adjusting the settings of protective devices, installing arc flash barriers, or providing training to workers. Fifthly, documentation. The results of the arc flash study are documented in a comprehensive report, which includes detailed diagrams, calculations, and recommendations. Arc flash studies are typically performed by qualified electrical engineers who have expertise in power system protection and safety. The results of the arc flash study should be reviewed and approved by the building owner or facility manager. In the context of adding a new fire alarm system to an existing apartment meter center, an arc flash study may be necessary to ensure that workers are protected from potential arc flash hazards when working on the electrical system. The arc flash study should take into account the specific characteristics of the fire alarm system and the potential for arc flash events during installation, maintenance, or repair. In summary, coordination studies and arc flash studies are essential aspects of electrical system safety. Coordination studies ensure that protective devices are properly coordinated to minimize the extent of any potential fault, while arc flash studies assess the potential hazards associated with arc flash and develop strategies to mitigate those hazards. Always consult with qualified electrical engineers to perform coordination studies and arc flash studies and to ensure that the electrical system is safe and reliable.